I'm Julie Forman-Kay, and I am a senior scientist and head of the molecular medicine program at the Hospital for Sick Children Research Institute in Toronto, and I'm also a professor in the Department of Biochemistry at the University of Toronto. I am interested in intrinsically disordered proteins, and most people may think about proteins, that's what you eat in the morning, eggs and whatever, gotta fuel your day. But proteins are the primary movers and shakers in biology, and the way they are constructed is like a necklace, beads on a string of amino acids. And many people understand the way proteins function, the way they understand human machines, like an engine, that you have a visible form, and that form gives rise to function. And proteins can go from this wiggly beads on a string necklace to form a rigid structure, fairly rigid, that gives function. But about a third of the beads, let's say, that make up the collection of proteins never form a stable structure, and they function in this very wiggly way, like a necklace would, making all kinds of conformations. And so I am interested in understanding how this large amount of wiggliness in biology can actually do function, and what happens when there are variants or mutations that cause disease in these regions of proteins. How do we understand how a difference in a wiggly bit of a protein can cause pathology? So disordered regions have pros and cons for NMR. So the dynamic interconversion of the different structures means, unfortunately, that the electronic environment of each nucleus, which is basically what's read out in an NMR signal, is averaged. And so the NMR signals often very much overlap on top of each other, which is not good. So this is called poor chemical shift dispersion, and the higher the resolution, the better able you are to resolve this problem with overlap. So that's where high field comes in particular. In the case of disordered proteins in normal buffer solution, their movement is often such that they can give very sharp signals. So the increase in sensitivity which high field brings is sometimes not needed for just some disordered regions. But often disordered regions have a variety of slower dynamic processes which lead to significant broadening of the signals and degradation of the spectral quality. And in that case, the sensitivity is very important. And especially in these condensed phases where it's like molasses, it's very, very thick. And so the molecules are tumbling very slowly. So if you put folded proteins in there, you can't even see the signals at all. But disordered regions have enough mobility, internal mobility, that you can see them, but you still need as much sensitivity as possible. So higher field is often very valuable for that as well.